Hello friend, we'll start with the second part of infrared spectroscopy. In this chapter, we are going to learn the factor affecting vibrational frequency and the applications of infrared spectroscopy. Before we proceed, what theoretical aspects we have learned in previous lecture? Just take down your notebook, write the things what we have learned, pause this video and write the things what we have learned in the previous lecture, and when you will finish, press this play button to continue with the today's lecture. I think all of you have finished. Now we will proceed with the lecture. Just play the video. So points we have covered in the last lecture. Regions of infrared spectra. We have studied that infrared region is divided in three main parts, that is near infrared, mid infrared and far infrared. So we are generally using micrometer ranges for measuring this infrared spectroscopy, that is 0.75 to 2.5 micrometer, then 2.5 to 50 micrometer is mid infrared region, and 50 to 1000 micrometer is a far infrared region. Generally, we are using wave number in infrared spectrum. So the wave number in centimeter inverse can be divided in three parts in this way: 13,000 to 4,000 near infrared, 4,000 to 200 mid infrared, and 200 to 10 as a far infrared. Now, the second point we have covered group frequency regions and fingerprint region. We know that we have divided the infrared spectrum in two frequencies, that is from 4,000 to 1,300 centimeter inverse, that is known as a functional group region or group frequency region, where exact functional group can be detected by using this region. The another region is between 1,300 to 400 centimeter inverse, that is called as a fingerprint region, which is a unique identifying characteristic for the various functional group. The next part we have studied, that is principle of infrared spectroscopy. In principle of infrared spectroscopy, we have studied that infrared spectroscopy requires two fundamental requirements, that there should be a change in dipole moment, different groups should be attached to the central atom so that there will be change in dipole moment, and frequency of vibration of atom should match with the frequency of bombarded beam. That we have studied. This is the minimum requirement of IR spectroscopy, that is to be called as a principle of IR spectroscopy. Then we have studied the Hooke's law of simple harmonic motions. This Hooke's law will give the frequency at which the vibrations are taking place. So we have studied in the Hooke's law
A pair of
the
atoms
various
joined by a
aspects. Okay, so in infrared spectroscopy, if we consider two atoms which are attached with a bond, and that bond can be considered as a spring for understanding purpose, the vibrations this is in the ground state, that V equals to 0, where there is no excitation. Now we can consider the mass differences of the atom which are attached. If the mass difference is more, greater mass difference will cause the lower frequency, the vibrations will be less, whereas the strength of your bond, strength of spring, will causes the higher frequency of the vibrations, that we have studied in the previous lecture. Then if the molecule or the atoms are vibrating in the ground state, and if they are bombarded with the infrared radiations, they absorb this radiation and start vibrating into the excited state. Okay, so this will be the V equals to 1 or V equals to 2. So these are the various vibrations that can be studied by using the Hooke's law, where today we are studying this Hooke's law and further part of the Hooke's law. So then we also studied the various types of vibrations produced in the infrared spectroscopy, that is stretching vibration and bending vibration. Stretching vibrations are of two types. One is your symmetric stretching vibration, another one is your asymmetric stretching vibration. And bending vibrations are again of two types: in plane bending vibration and out of plane bending vibration. In plane bending vibrations we have studied rocking and scissoring. Out of plane bending vibrations we have studied wagging and twisting. So these points we have covered in the next lecture. Then one more point we have covered, that is the degree of freedom. Degree of freedom means how much vibrations can occur in a molecule or in an atom. Okay, in a molecule, how many atoms are attached, whether the molecule is linear molecule or non-linear molecule. Accordingly, that there are the two formulas 3n minus 5 for linear molecule. We have studied the example of carbon dioxide, okay, CO2 having the three atoms. So 3 into 3, that is 9 minus 5, it will produce 4 fundamental vibrations. Similarly, for non-linear molecule, there are 3n minus 6 degree of freedom. We have studied one example of benzene. Okay, so where 30 vibrations will be there, means 30 peaks will be produced in the IR spectrum of benzene. So this we have studied in the previous lecture. Today we have to study the factors affecting vibrational frequency. Before we go to that vibrational frequency factor, I will just show you one infrared spectrum of formaldehyde. Okay, so we have studied the Hooke's law, the degree of freedom. Degree of freedom will give you the information regarding how many bands will be produced. Now, if you see the infrared spectra of formaldehyde, you can count this how many bands are produced in infrared spectrum of formaldehyde. 1, 2, 3, 4, 5, 6. It is producing 6 band. Now, what is our formula? 3n minus 6. Okay, so now see here how many atoms are there in this formaldehyde molecule. 1, 2, 3, 4. 4 threes are 12. 12 minus 6 means it will produce 6 bands. Out of this 6 band, this CH2, there will be the symmetric stretch for CH2 and there will be the asymmetric stretch for CH2. Also, the CH2 will show you 3 bending vibration. One is scissoring, one is rocking, and one is wagging. And one more atom is there, that is C double bond O. This functional group shows you a sharp peak at 1750. In this way, this degree of freedom will inform you how many peaks will be produced in the spectrum. Now, this position of peaks is constant for a particular functional group, but it also varies depending upon the various factors which are responsible for the position of these peaks in the spectrum. You recall the part what we have learned in your UV spectroscopy. In UV spectroscopy, you are knowing that we are observing the lambda max, and the value of lambda max may shift towards the higher side or towards the lower side of the in the UV spectrum. Okay, if it is shifted to the higher side, that is towards the red side, it is known as the red shift. If it is shifted towards the lower side, it is known as a blue shift. Okay, hypsochromic shift. So we know that various factors are there like solvent and other hypsochromic and hyperchromic groups which will be shifting the lambda max position. Similarly, here also in vibrational spectroscopy, the position of this peak will change or it will be shifted. So various factors affecting vibrational frequencies. So we have studied the Hooke's law of the simple harmonic motion by taking the examples of ball and spring model, that vibrations are directly proportional to the strength of the spring and the mass differences. Okay, so this Hooke's law can be written as V equals to 1 by 2 pi c under root F by mu, where F is a force constant that we can call it as a spring tension, and mu is the reduced masses of the atoms which are attached to this spring, and c is the velocity of light. If you know the velocity of light, if you know the force constant, and if you know the reduced masses, you can calculate at which frequency the atoms will absorb in IR region. Okay, so this is by the Hooke's law. The value of absorption frequency is shifted if the force constant of the bond changes with its electronic structure. So this value depends upon the electronic structure of your molecule. So what are the various groups attached to that atom? Frequency shift also take place on working with the same substance in different state. So whenever we are showing the IR spectra, we have to state the physical state of the matter, whether it is a solid, liquid, or vapor. Okay, so because this physical state will also shift the IR spectrum position, IR peak position. A substance usually absorb at higher frequency in vapor state as compared to the liquid and solid state. Because of the vapor state, there is a less collision between the atoms, and that leads to the change in their absorption frequency. There are four main factors affecting the responsible for shifting the vibrational frequency from their normal values. These are coupled vibrations, Fermi resonance, electronic effect, and hydrogen bonding. So these four parameters will decide the shift in the vibrational positions or the appearance of particular peak in the IR spectrum. So one by one we will study. First one is your coupled vibrations. Coupled vibration means we know that two atoms are vibrating nearby. Okay, so when these two atoms are vibrating nearby, they may produce interaction of their vibrations, and that may leads to the appearance of one or more peak into the IR spectrum. You can take the example of your CH, okay, CH bending. So an isolated CH bond has only one stretching vibrational frequency, whereas in methylene group shows two stretching vibrations of symmetrical and asymmetrical atoms. Because of the mechanical coupling or interaction between CH stretching, vibration in CH2 groups are shown. Asymmetric vibrations occurs at higher frequencies or wave number than symmetric stretching vibrations. Okay, so the positions will change whether it will be the asymmetric vibrations or symmetric vibrations. These are known as coupled vibration because these vibrations occurs at different frequencies than that required for an isolated CH stretching. A strong vibrational coupling is present in carboxylic acid. One more example is your carboxylic acid. So, acid and anhydrides in which symmetrical and asymmetrical stretching vibrations appear between the region 1720 and 1825. So, if you see the spectrum of this carboxylic acid, you can see that there are the two peaks produced in the carboxylic acid, and these are due to the coupling of the atoms. Then the next factor responsible is your Fermi resonance. Fermi resonance, that is interaction which occurs between fundamental and overtone or combinational bands, are known as a Fermi resonance. So Fermi resonance, before you go towards the Fermi resonance, you should know what is fundamental and overtone vibration. Fundamental vibrations means V equals to 0 or V equals to 1. Okay, so vibrational level is in the, if it is in the ground state, that is V equals to 0, no vibrations. V equals to 1, it is in the fundamental vibration state. And when it is going towards the higher level, that is V equals to 2, that is known as the overtone vibrations. Okay, overtone vibrations. Such vibrational coupling you can observe in the instruments. Okay, if you are playing the guitar. Okay, so when you play the guitar with the multiple strings, okay, so when you touch one string, the other string also start vibrating, and the vibration of these two strings couples with each other, and that is known as a Fermi resonance. This phenomena can be observed whenever two fundamentals or a fundamental and overtone bands are have nearly the same energies. Here, molecule transfer its energy from fundamental to overtone and back again, and so that the each level become partially fundamentals or partially overtone in the characters. As a result, two strong bands are observed in the spectrum instead of the expected strong and weak bonds. Okay, so there should be one strong band and one weak band. Rather than we will get this two strong band, and that is due to the coupling of the vibrations of two similar atoms. You can take the examples of carbon dioxide. It is normally shows fundamental bands at 1337 centimeter inverse and overtone at 1334 centimeter inverse. So this is known as a Fermi resonance. The vibration of the large amplitude produced by a relatively small vibrations you can distinguish between the Fermi resonance and coupled resonance, okay, coupling of your vibrations. So Fermi resonance occurs at the excited state, therefore it is different than the coupling one. Okay, so what is overtone? Overtone absorption bands are the results of forbidden transitions arising from the ground vibrational energy. Okay, zero V equals to 0 to V equals to 1 or V equals to 2. They are less intense than the corresponding absorption bands. Okay, combination bands appear between 1900 centimeters and 2500 centimeters are results of the vibrational interactions. Their frequencies are the sum of multiplies of each integrating frequencies. So this is known as a fundamental vibration. So you can have C double bond or CO2. Okay, in the carbon dioxide, we can see that there may be the asymmetric stretch or there may be the symmetric stretch. So this symmetrical stretching vibration of carbon dioxide in Raman spectrum shows band at 1337 centimeter inverse. The two bands vibration are equivalent and absorbed at the same frequencies of 667.3 centimeter inverse. Okay, so that is known as a Fermi resonance. The first overtone of this is 2 into 667.3, that is at 1334.6 centimeter inverse. Okay, that is a Fermi resonance has been occurred. Okay, so this is the second factor affecting your vibrational frequency. The third one is your electronic effect. So what sort of the electronic effect might be there? So that depends upon the various groups which are attached in the atoms. Change in the absorption frequency for a particular group take place when the substance in neighborhood of their particular group are changed. Okay, example, the frequency shifts are due to the electronic effect, which includes either there will be the inductive effect, there will be the mesomeric effect, or there will be the field effect. So what is inductive effect? Inductive effect you can see in the case of the formaldehyde. Okay, in case of the formaldehyde, you may see the C double bond O stretch at 1750 centimeter inverse. But if you take the acetaldehyde, this hydrogen is replaced by one more CH3 group. The shifting towards the lower side will be there and the band will appear at 1745 centimeter inverse, shift by 5 centimeter inverse value. Okay, so now further you go with acetone. Okay, so in case of acetone, instead of CH3, you are connected with the CH3. Acetone group is attached. Okay, so now this CH3 will result in what? So that will again shift the absorption position towards the further less side, that is 1750 centimeter inverse. This is called as an inductive effect. What is the mesomeric effect? So more will be the conjugation, less will be the bond strength, and lower will be the wave number. Okay, example, in methyl vinyl ketone, acetophenone, stretching of C double bond O appears at 1706 centimeter inverse, whereas in the acetophenone it appears at 1693 centimeter inverse. So that is known as a mesomeric effect. Okay, so acetophenone, we have compared methylene vinyl ketones and acetophenones. That is your mesomeric effect. Similarly, the third factor affecting is your field effect. Okay, in order ortho substituted compounds. Okay, so this field effect depends upon whether it is ortho, meta, or para. So in ortho substituted compound, lone pair of electrons on two atoms influence each other through space interactions and change the vibrational frequency of the both groups. Okay, so that is called as a field effect. Now we'll just go towards the last factor which is affecting the vibrational frequency, that is known as a hydrogen bonding. Okay, so a hydrogen bonding will also shift the position of a IRP towards the higher side or towards the lower side. It occurs in any system containing a proton donor and a proton acceptor. Okay, so either it is XH, so X may be OH or it may be NH, also whatever group may be there. So this is either it should have a proton donor and a proton acceptor value. The stronger the hydrogen bond, the longer the OH bond. Okay, so whatever OH bond, broad OH bonds we are observing in case of IR, the lower the vibration frequency and broader and more intense will be the absorption bands. The inner stretching frequency of amines are also affected by hydrogen bond as they that of the hydroxyl group. Okay, whether that atom molecule contain NH group or OH group. But frequency shift for amines are less than that of the hydroxyl group, and that is due to the hydrogen bonding. Because nitrogen is less electronegative than the oxygen, so the hydrogen bonding in amine is weaker than that of the hydroxyl compounds. Okay, there are two types of the hydrogen bonding interactions. One is intermolecular hydrogen bonding, which gives rise to the broad bands. Okay, so there will be the broadening in the bands, and in the second one is the intramolecule. Intermolecule means within the same molecule, if H and OH groups are present, so they may produce a hydrogen bond. And in intramolecules, two different molecules, and there is a formation of hydrogen bond between these two different molecules. So that is the intramolecular hydrogen bonding, which gives the sharp and well-defined band. Okay, so these are the various factors affecting your IR frequencies, whether at which position the IR will be appearing. So as per our syllabus, this much discussion is sufficient. If you are more interested in checking the structural elucidation process by using IR spectroscopy, I have already uploaded a different presentation on YouTube. You can go through it. Now we'll start with the next part of this today's lecture, that is advantages of your IR spectroscopy. So when you are thinking of the advantages of IR spectroscopy, so first advantage we can see, that is a high scan speed rate. So infrared spectroscopy can get information for the whole range of frequencies simultaneously within 1 second. Okay, so therefore IR can be used to analyze a substance that is not very stable and finish the scan before it starts to decompose. Many substances are unstable, they needs to be analyzed within a very small period of time, so that can be done by using IR spectroscopy. The second advantage of IR spectroscopy is a high resolution. The resolution of general prism spectrophotometer is only about 3 centimeter inverse, but the resolution of infrared spectrometer is much higher. For example, the resolution of grating infrared spectrophotometer could be 0.2 centimeter inverse. The resolution of FTIR infrared spectrophotometer is again 0.1 into 10 raised to minus 0.005 centimeter inverse, means very accurate resolutions we will get with the FTI. So whenever we are studying the instrumentation, we will discuss this matter there also. Then the next advantages of your infrared spectroscopy is the high sensitivity. With Fourier transform, that is FTIR, the infrared spectrophotometer doesn't need to use the slit and monochromators. They are using the interferometer for selection of the wavelength rather than the prism and monochromators, as we have learned in the first lecture. In this way, the reflection spectacularly will be increased and loss of energy in analysis process will be decreased. Therefore, energy that reaches the detector is large enough, and even very small amount of the analyte could be detected. So that therefore it is a high sensitivity. A small samples can be detected by using your infrared spectroscopy. Even 1 raised to minus 10 grams. Okay, very small quantity can be detected. Then the next application is wide range of this infrared spectroscopy. Infrared spectroscopy could be used to analyze almost all organic compound because they contain the functional group, and due to the presence of the different atoms, they will show the change in dipole moment, and therefore they can be detected. Some inorganic compound can also be studied by using this IR spectroscopy. It has a wide range of application in both qualitative analysis and quantitative analysis. Also, the sample of infrared spectroscopy doesn't have phase contrast. It could be a gas, liquid, or solid. Okay, so you can handle the sample in any physical state. That is the first applications or wide range that can be utilized. Okay, large amount of informations we can get from the infrared spectroscopy, mm, because lot of structural information of analyte such as type of compound, functional group of compound, stereoscopic structure of compounds, the number and position of subsequent group, and so on. So this information is available when you are doing the infrared spectroscopy, and depending upon the available information from the functional group part and fingerprint part, the infrared spectrum has become a great importance in the process of structural elucidation. Structural elucidation means detecting the structure of compound. Okay, so that is the another important application of your infrared spectroscopy. Another application, it is a non-destructive method. When the sample is very costly and we don't want to waste our sample, so we can go for infrared spectroscopy because it is a non-destructive technique where we can preserve the samples or we can reuse the sample. One more application of infrared spectroscopy is a sample constraint. Okay, sample constraint means infrared spectroscopy is not applicable to sample that contain water, since this solvent strongly absorb the IR radiations. That is that you can also take in the disadvantage that sample of your infrared spectroscopy should not contain any water. Okay, so again the Raman spectroscopy was developed where the water samples can be the solutions of in the water can be taken. Okay, and the second disadvantage of your IR spectroscopy is the spectrum complications. Spectrum complication means the IR spectrum is very complicated and the interpretation depends on lot of experiences. Sometimes we cannot definitely clarify the structure of compound just based on the one signal. Okay, so by just using one spectroscopy, you cannot detect the structure of any compound. So we have to combine all spectroscopic technique together to come to the conclusion of the structure. We have to combine the mass spectroscopy, NMR spectroscopy to know the structure of compound. Okay, and cannot be used for the quantifications because this is not the quantification tools as you are using in the UV and visible. Infrared spectroscopy work well for qualitative, not for the quantitative analysis of large variety of sample, but quantitative analysis may be limited under certain conditions such as very high and low concentration can be studied by using this IR spectroscopy. So now we will stop here and you can see the third video to be continued in the next time, so which will cover the instrumentation and sample handling techniques. Thank you very much. Thank you for seeing this lecture.